Okay, class, welcome to Physics 203, class number 14 on probability and wave functions. And we're going to continue here in understanding our transition from classical to quantum physics, developing the ideas of the de Broglie wavelength and of the Heisenberg uncertainty principle and wave packets that we did in previous classes. So we're going to start to get a handle on probability and wave functions by an analogy with light. Um, so in the case of light, we have the two-slit experiment, which we looked at previously, where we send light through a double slit, and it diffracts and forms a diffraction pattern of alternating light and dark bands on a screen. And we know and we can measure that at points where the light is strong, the electric field amplitude is large, and where the light is weak, the electric field amplitude is weak. And in addition, if we make the light very, very faint, we can actually see the individual counts of photons building up slowly, 20 to 100 to 500 to 1,000 to 4,000, building up the interference pattern. So more precisely, it turns out under the wave description, the intensity of the light is a constant, epsilon naught, the permittivity of free space, times the speed of light times, and this is the important part, the square of the electric field amplitude. So the guiding wave, the electric field amplitude squared, tells us the intensity of the light at a given point. Meanwhile, in the particle description, the intensity would be n, the number of photons hitting in a certain area, times hf, the energy of each photon. So we see this correspondence between the number of photons, or the chance of a photon hitting, and the square of the amplitude. So we can say that from this analogy with light, the probability of observing a photon is proportional to the square of the electric field, because we get the number of photons we get here, n, is proportional to the intensity, and the intensity classically is proportional to the square of the electric field. Okay, so having established that, let's talk about the wave function, which is the equivalent of the electric field for a material particle. Remember, we talked last time about, in the context of the Heisenberg uncertainty principle, about using a wave packet, psi, which we called psi, which was composed of many wave numbers, many wavelengths or wave numbers, k, to represent a traveling quantum particle. And recall from last time that the velocity of the particle is the group velocity, the velocity that the whole packet moves, not the velocity that any of the component wave numbers k are moving within it. So by analogy with the electric field and photon case we just looked at in the two-slit experiment, we take the square of this guiding wave, psi, to represent the chance of finding the quantum particle at a given position x at a time t. So for example, as this packet moves across, the wave function is greater in the center, so there'd be a greater chance of finding the particle in the center of the wave packet than on the sides. Interestingly, as we'll soon see when we get into the Schrodinger equation next class, psi, this wave, what we call the wave function, psi, is actually a complex number. And this is needed to describe the full range of quantum behaviors, the interference behavior, and It doesn't mean that any physical quantity is complex, that is, has an imaginary part, but it's just part of the mathematical notation needed to capture the full range of quantum behaviors. So then the square of psi, psi x of t squared, can actually be written as this complex number, the wave function, times its complex conjugate, that is, dropping the x and t, psi star psi. So let's review this a little bit in case you're rusty on complex numbers. So we have, I'm claiming that psi is a complex number. It's a, it would have a real part a plus an imaginary part b times the I, the which is the square root of -1, the unit imaginary part. So that's represented here, where we have a real axis, an imaginary axis. Psi is this sort of vector in the plane, and A is the real part. It's parallel to the real axis, and B is the imaginary part. So it'd be A plus B times I to mark the imaginary part. And then the complex conjugate we get just by switching the sign of the imaginary part. So instead of going plus BI, having plus BI being in the positive imaginary direction, we're in the negative imaginary direction. So we have a minus BI. So it's just reflected over the real axis. Algebraically, psi star psi would be a minus IB. That's down here with, again, the IB minus IB, meaning the vertical component pointing down, the imaginary axis, times a plus IB. And expanding this out, we get a squared plus IAB minus IBA. I'm just doing the algebra technique FOIL, if you remember that. First outside, inside, last, times, or minus I squared B. But I is the square root of -1, so I squared is -1. So we have minus 1 B squared. So we get psi star psi is equal to a squared plus b squared. And that is the square of the magnitude of psi, because the magnitude of psi, according to this geometry, with side A and side B, would be the square root of a squared plus b squared. So a squared plus b squared would be the square of the complex number psi. Okay. So we'll get more into, we'll describe more, you'll see more how it's, the wave function is complex as we move along. Probability density and normalization. So we have this wave function psi, and this is the two-slit electron fraction experiment, where we get a electron which can sends waves out which interfere and can go through one slit or the other. And we can record we record an interference pattern on the screen here, or on the detector here. And psi squared, which is associated with the electron, since it's a material particle, is called the probability density. And it measures the likelihood of finding a particle, or the particle, this electron, near a given position at a given time. Okay, so let's get a little more explicit mathematically with that. More precisely, what we would write down is that P of y dy, where P is the probability density as a function of y, and dy is a small interval, is equal to psi as a function of now y, since it's the vertical direction, and t squared dy. So we can see that psi squared is playing the role of the probability density. What does probability density mean? It means to get a probability, you take the value of p at a given y and you multiply by a small interval. And that makes sense because um, uh, the larger the interval of y that you choose, the more chance there is that a particle is going to fall into that interval. So it makes sense that that we use the probability density, the probability per unit length times the length dy to represent um, our total probability. And this interpretation of the wave function as the probability density, indicating where it's likely to find most likely to find the particle and where not, is due to Max Born, a German who um, later emigrated to England and was one of the great contributors to the foundations of quantum physics. And once we have this idea of probability density, since each electron that comes through here has to wind up at some value, has to be, if it irradiates a photographic plate, has to wind up at some value of y, the sum, or speaking, since this is a continuous function, the integral of the probability density over all these y values must be equal to 1, because that would represent the chance, if we integrate over all y values, that's the chance that the particle can be found anywhere, that is somewhere between its lowest value and its highest value. So it has to be somewhere in between there. So we write that as the integral from minus infinity to infinity of the probability density is equal to, which is equal to, according to Max Born, the square of our wave function. Probability density is the square of the wave function is equal to 1. And that's called normalization. And we'll be seeing more examples of this as we develop our quantum physics. Now I'd like to talk about the Copenhagen interpretation of the wave function. This was a very influential take on quantum physics that developed in the 1920s, kind of a system of making sense of this new wave function, this new guiding wave for particles, and these new surprising behaviors that were being seen. So it consisted of Bohr's complementarity, which, remember, is the idea that we can describe we can't describe the same particle or the same entity as both a particle and a wave. It has to either be interpreted as a wave or as a particle in different circumstances, and both treatments are necessary, wave and particle. Plus the Heisenberg uncertainty principle, which we talked about last time, which limits our ability to know the position and momentum of a particle at a given time. Plus Born's take on the wave function psi, which we just talked about. That is, that it expresses the that the square of it represents the probability of finding the particle at a given place. And all these together, this kind of system is known as the Copenhagen interpretation. Why Copenhagen? Well, Copenhagen here in Denmark was an early center of atomic and quantum physics, mainly under the influence of Niels Bohr in the Niels Bohr Institute, where several of these physicists and others came to visit and formulate this this first take on or this philosophy of the wave function and what it meant. So to put it another way, or to summarize, the wave function, the guiding wave for a particle, evolves according to a dynamical equation. That's the Schrödinger equation, which we will get to next class. The results of a measurement are probabilistic, according to Born's take on the wave function. That is, that psi squared represents the the chance of finding a particle at a given place. So that means it's probabilistic because it could be found in a range of different places. And all that we can talk about are the probabilities of finding it in one place or one area versus another. And thirdly, that other possible measurement, once a measurement is made, one of these possibilities is picked following these probability laws, and other possible measurement results are lost, never to be seen again or to recovered. So these are some strange ideas. And it turns out that there were some dissenters here. You recognize this guy. This is Albert Einstein. And this, you might not recognize, is Schrödinger of the Schrödinger equation, who we'll be looking at quite soon, which we'll be looking at quite soon. And Einstein didn't like what Heisenberg and Born and Bohr were saying and the Copenhagen interpretation. He said, God does not play dice with the universe. He didn't believe that the results of measurements should be probabilistic. He believed that something should determine where a particle was being found, even if we couldn't immediately identify what that something was. So Einstein was never happy with the Copenhagen interpretation. But today, the mathematics and predictions of the Copenhagen interpretation work quite well, and it's the most common take on quantum physics today. There's another take on the Copenhagen interpretation. There's another take on quantum physics called the many worlds interpretation, which is very interesting. It says that other possible measurement results are not lost, never to be seen or recovered, but in fact branch out into a series of accumulating universes or realities, so that each set of measurements, all measurements, are actually realized, but they branch out, and each measurement is the precursor of a different starts a different branch of the universe. So that's kind of far out stuff. Still very speculative today. We'll close with an important quantum system, the particle in a one-dimensional box, just to give a definite example of using this, first example of using this wave function. So here's a specific example. There's a restricted area. This is an integrated circuit, as you can kind of guess from the picture, of very small size. And there's a restricted area for electrons on this integrated circuit, which is this little line here, which we can call a nanowire. Nano because it's nanometers, and wire because it's long and thin. And you can see represented here, this is actually, nothing is actually fully one-dimensional in reality. There's, this thing is, it's very long and thin, but it's not a one-dimensional line. But this represents, these 5 humps represent the wave function, the square of the wave function for the electron probability on this nanowire. So analyzing this on our first pass, we can say that we can take this nanowire from one end to the other and represent it along a variable x that goes from 0 to L. And the particle, in this case an electron, but whatever particle it is, can't leave this area, which we're calling a box. So that means the wave function must go to 0 at the ends, 0 and L. Because remember, the wave function has to be 0, the wave function is associated with how likely it is to find the particle. And so if it's impossible to find the particle to the less than 0 or greater than L, then at 0 and L, the wave function must go to 0. So looking at, it makes sense to look at wave-like solutions since we're dealing with a wave function. And looking at wave-like solutions, we see that there are different possibilities, sinusoidal possibilities for the wave function going to 0 at the endpoints. This is one which goes through half a wavelength. This is one which starts at 0 and goes through a full wavelength. This is one which goes through 1.5 wavelengths. This is another which goes through 2 wavelengths, and so forth. So we can say that n lambda over 2 is equal to L for n equal 1, 2, and 3. Taking example n equal 1, lambda over 2, the wavelength over 2 would be L, because the wavelength of this would actually be twice the length of the box. And for n equal 2, we'd have 2 lambda over 2, or lambda equals L, and we can see that this goes through 1 wavelength lambda. Solving for lambda, this becomes 2L over n. So we get a wavelength which decreases as the number of oscillations n in the particle increases. So we can actually, given these given these wave functions, given these wave functions, we can actually find the energies of the states 1, 2, and 3 using our knowledge of kinetic energy and the de Broglie relationship, which we learned several classes ago. So how does that work? Well, you remember that energy is, the energy here is kinetic energy. We're not dealing with any forces or potential energies. Remember that that's 1/2 mv squared. That can be written as p squared over 2m, as you can verify if you plug in mv for p. It reduces to 1/2 mv squared. But then using the de Broglie relationship, p is equal to h over lambda. So this becomes 1 over 2m times h squared over lambda squared. So that's the first step. Then the second step is to use the fact that lambda, because the wave function has to come to 0 at each end of the box, because the particle can't be found outside the box on either side of the box, lambda only takes on certain values, 2L over n, where n equal 1, 2, 3, etc. So these certain allowed wavelengths, resonant frequencies, almost like a wave on a string with 2 fixed endpoints on a string. The mathematics is the same. So if we substitute in for lambda here in the denominator, we have h squared over 2m times n. Lambda is 2L over n, but if we reciprocate that, we get n over 2L squared. Simplifying everything, we get n squared times h squared over 8ml squared. Okay, where n is equal to 1, 2, 3, etc. So the key takeaway from this is that we get a set of allowed wave functions in this confined space, this one-dimensional box, and the energy associated with each of these wave functions goes up as the square of the number of oscillations in the wave functions, and this is called quantization. That the energy can take not any value, but only certain allowed values, n equal 1, 2, and 3, and n here is called a quantum number. And just to emphasize again, the so-called quantization of energy levels comes from what we call boundary conditions. The fact that the wave function had to go to 0 at both ends of the um, box. And so we'll see this same solution here, which we sketched out roughly, assuming sinusoidal solutions, more officially when we introduce the Schrodinger equation quite soon. So in conclusion, we have we've introduced the idea of the wave function and the interpretation of the square of the wave function as the probability of finding a particle in a given time and place. We've looked at the Copenhagen interpretation involving the uncertainty principle and principle of complementarity, and this interpretation of the wave function. We've looked at one modern alternative to it, and then we've looked at this particular system to get an idea of what it means, how it leads to quantization, which is what gives us the name quantum. So I hope you've found this interesting, and looking forward to seeing you in class. Thanks very much.